This is Dr. S.P. Harsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 29 on the course of the strength of materials, and this course is developed under the National Program on Technological Enhanced Learning. Prior to start this course, which is basically on shearing stresses of the different cross-sectional beams, like you see if we have a rectangular cross-section or if we have an I-section beam, then how we can find like the maximum the shear stresses in those things, and how we can say that if we have the cross sectional beam of any kind, then shear stress distribution is of this kind and all like. So this all information which we are going to discuss in this lecture. But prior to start that, you see, we would like to focus that what we have discussed, because you see we are going to discuss we are going to use all those theories which we have discussed in the previous lecture. In the previous lecture, you see, we focused on two different issues of a beam. One was the banding, pure banding. When pure banding is there, for that you see we derived one equation that was this sigma by y, where the sigma is the banding stresses. So sigma by y is equals to m by I, and m is the applied banding moment, and I was, you see, the mass moment of inertia was there, or we can say the second second moment of area. So like we can distribute according to what kind of sections are there. So sigma by y equals to m by I equals to E by R, and E is the Young's modulus of elasticity. So whenever the pure banding is there, so in that we also assume that the plane will remain plane even before and after the banding. So that means, you see, there is no change in the plane section. So that kind of discussion which we made, and then we solved some of the numerical problem, that if we have a cantilever beam, or if we have a simply supported beam, and if it is loaded with a single, like this uniformly distributed load or point loads are there, then how like we can get the these bearing stress, this all bending stresses for those things, and you see how the distribution of these bending stresses are, because you see like in the flanges, in all those things, either we have this fibers of top fibers or lower fibers, they are experienced with the different kind of tensile and the compressive stresses, which are the flexural stresses. So these discussion which we made in the previous lecture, in the first part of that, then we found that if the shearing stresses are there, and due to the shearing stresses it causes wrapping action. So whenever the wrapping is there in the beam, then the beam will not be exactly the plane of the beam, whatever you see, like under which the fibers are there and they are experiencing with those kind of stresses, they will not be remain exactly as the same of the plane as before and after of these stresses. So that means, you see, whatever the assumption which we made in the banding, whenever the pure banding is there, here it is violating of some nature. So sometimes you see, if we are saying that if the uniform banding stresses or non-uniform banding stresses are there, or this kind of deformations are there due to the banding and the shearing, then we can't use those like the sigma by y equals to m by I equals to E by R. But due to the practical applications, we found that they are approximately equal, means the wrapping effect has some impact on those things, but these equations are somewhat valid for non-uniform as well as the uniform banding distribution. So in that case, you see, we can use the sigma by y equals to m by I equals to E by R. Then in the later section, you see, we discussed that actually if we want to analyze the shearing stresses for any section, then certain assumptions are there, and those assumptions we applied for just to like easy of our calculation, because you see if we are using all those the real theory, then it complicates, you see, like the basic banding, because here in that section we the shearing forces are there, at the same time the bending moments are there, and you see it complicates the system. So we need to if we want to analyze those things, we need to put certain assumptions to make it convenient for our easy of the analysis. So for that, you see, after applying all those assumptions in the shearing of the beam which we discussed, three assumptions, then you see we found that the sigma, whatever the tau, which is the this shearing stress is equals to the F, which is shear force. So F into A into Y divided by I into Z, where F is the shear force, and always you see shear force gives you the clear direction about the sign convention, that how the the beam will behave under the action of these shear forces. A is the area of whatever you see, the area which the concerned area, or we can say the matter of concern is there on that particular part, and then Y is the distance of the centroid from the neutral axis. So here you see This is a pretty, like typical thing is that when we are talking about a y and y bar generally we are taking, like the distance between those two axes, and y is the distance. You see, generally we are talking about that where the shear stress is which we want to calculate, because if you are saying that, yeah, let us say above from the neutral axis at, just calculate at 10 millimeter from neutral axis above or below or some of the distance, it's pretty easy to calculate once you know the y, and once you know the relation between the centroid as well as the neutral axis, then it is pretty easy to stabilize those stresses within that object, because you see it's a kind of distribution, and once you know, here the centroid is occurs, or here the neutral axis is there, then it's pretty easy to make the distribution of this kind of stresses, because you see ultimately, the distribution is very very important for any kind of design for a beam under any kind of loading particular. So, and then so F into A into Y divided by, we have I into Z, and I is the the second moment of inertia, which in the previous sections we discussed that actually it can be calculated by summation of this y square into dA. So this is the square term is there here into the multiplied by the area. So that's why it is known as the second area of moment, or we can say that it is by integration also, because if we have a regular structure, then we can also calculate this kind of thing by integration. Into Z. Z was, you see, just the the width of a cross sectional area, that actually what exactly the area which the cross sectional part of the object we can say. So width is given by this Z. So you see here it is influencing, means the shearing stresses which we are calculating, it is always influencing by the shear forces and this dimensional parameter of that. So this is which we discussed in the previous lecture. Now in this lecture we've basically focused on first that if we we have the shearing stresses for this kind of thing, and we are talking about the area. So important thing is that actually what exactly the cross sectional area is, because in these shearing stresses you found that it not only depends on the shearing forces, but also it depends on that what exactly the area is or the dimensional parameter is. So first of all, our main intention is just to focus that whatever the area which we are concerning. So that's why you see here in this lecture our main focus firstly is on that what is the cross sectional area of a beam is like, and that's why you see we are going to concern about the two main areas. One is the rectangular cross section, and second is the I section is there, and then you see we will check it out that actually how this shear distribution is going on in that. So here it is, you see first the shear stress distribution in typical cross sections. So let us consider for a few examples to determine the shear stresses distribution in a given cross section. So first cross section, as I told you that actually we are going to use that the rectangular cross section. So considering this rectangular cross section which has the height we can say is a diameter or we can say this dimension d, and then you see we have a breadth, that is the b is there, and in this you can see that actually since it is a symmetrical structure, so in that we can easily calculate that where the neutral axis is existing. So exactly at the half of, means that d by 2 we have because it's a symmetricity is there, there is no any kind of non-uniformity is there in the structure, so we can easily put those things. So here at d by 2 we have the neutral axis, you can see on your screen that it is the dotted line is showing the neutral axis, and then now you see we just want to focus on a small element, and then you see generally we are using that the integration of that, so that whatever the deformation or whatever the kind of shearing stresses which are occurring in this kind of structure, it can be simply simulated for entire structure once for a small segment. So for with the using of that segment, you see again we are using that, okay, if we have a segment or we can say the strip, okay, which is just the distance of y. So you see here this from the neutral axis we have the distance of this strip is y, and you see this centroid of the strip is exerting at somewhere, and the distance for between the centroid of this strip with the or with this rectangular section to the neutral axis is y bar. So here you see you can clearly visualize the difference between the y and y bar, and as I told you, see this is the real difference, and in the shearing stresses we are using those things particular, and then as I told you, this is just the total is d, so it is d by 2 here there, so this is d by 2, and this is the total is this y. So this distance will be clearly the d by 2 minus y. So we have the height of this strip is d by 2 minus y, okay, and there is a point A where the centroid is located. So now just keep these information in your mind. We would like to calculate the shearing stresses for that. So A is the area of the cross section generally which we are using, like cutting by the line parallel to the new axis, this neutral axis, that is the y bar, and y bar is real the distance, as I told you, between the centroid of the this cross sectional to the neutral axis. And then you see, with the using of that information, we have the shear stresses is nothing but equals to F into A into y bar divided by I into Z, as we discussed. And now since we are talking about that strip in which the breadth is B and the height was D by 2 minus Y, so you can calculate the area because it's a simple rectangular cross section is there. So it is nothing but equals to B into D by 2 minus Y. So now we have the cross sectional area of this. We have the shear stresses. In this shear stresses, now what we need y bar. So again you can calculate the y bar, because y bar is exactly just existing in the in the midway of the strip. So now half of, because you see we have the distances from the neutral axis is this y bar. So y bar we can calculate it just by midpoint of those things. So first of all, we have the strip this height, that is D by 2 minus Y, and the total from that to that we have the Y. So if you remember those things, we have the total height of these things is Y plus D by 2 minus Y. So if we divided by 2, then we have the exact location where the centroid is locating. So y bar is nothing but equals to D by 2 minus Y, one segment, plus Y divided by 2. Or if you manipulate those things, then we have the y bar, which is the distance of the centroid to neutral axis, is equals to half of D by 2 plus Y. So now you see we have area, we have y bar. So in this shear stresses, what we need first now I. Since it is a rectangular cross section, so I can be easily calculated, and the neutral axis passing from the diameter. Okay, just keep this thing in mind, just in this D, basically it's a height, not diameter, it's a height D. So now we have the I is BD cube by 12, and then one more parameter is left, that is the this width. So width is, again you see it is given as B, so Z is equals to B. So now keeping those parameters in our mind, now we just want to put those things in our first formula, that is shearing stresses is equals to F into A into y bar divided by I into Z. So now if we keep those things, then what we have in place of F, that is again shear forces are there, which is pretty common, and then we have the area. Area we calculated B into D by 2 minus Y, so we just simply put those things, and then we have the y bar, which we have calculated the half of D by 2 plus Y divided by I, which is BD cube by 12, and we have the B, that is Z. So now you see, by manipulating those things, what we have after calculation, we have F by 2, that is the shear stresses, is equals to F by 2 inside the bracket D by 2 whole square minus Y square divided by BD cube by 12, and again if you keep those things on top of side, then we have 6 into F D by 2 whole square minus Y square divided by BD cube. So if you look at those the parametric, then you will find that you see the shear stresses for this kind of rectangular section is absolutely depends on that how these the dimensions are varying. That means you see here that Y, that actually that Y is always a varying distance, that how much depth you want to use, and what is the distance is there from the neutral axis to that strip. So that is the y square, and D by 2 is always you see that where how much height which we are using for our cross sectional area, the cross sectional section, and then we have the BD cube. These are also the dimensional parameter of those things. So here if you look at this picture, we will find that we have a parabolic kind of distribution, because it's a square term is there. So shear stress is also, whenever you see the kind of this the distribution is there in the rectangular structure, then you will find that we have a kind of this parabolic distribution is there. So with that parabolic distribution of the shear stresses with Y, now our main intention is to find it out that now with this parabolic distribution, where the minimum and where the maximum shearing stresses are occurring. So the maximum value of shear stresses would obviously be at the location Y equals to 0. That means you see, now if we are keeping Y equals to 0, that means exactly it is somewhere, if you visualize this Y equals to 0, then you will find that there is no distance from neutral axis to that strip. You are simply deleting. So now by putting those values, what we have the tau maximum, which is the shear stress maximum, is 6F by BD cube. This was the constant parameter, and we had D by 2 whole square minus Y square. So Y is gone, so we have D square by 4, or we can say by manipulating we have 3f divided by 2bd. So tau maximum is equals to 3f divided by 2bd, and the value of tau maximum occurs at the neutral axis because we are already eliminating these y. So there is no gap between the neutral axis and the the height of the strip. So now this tau maximum is occurring at the neutral axis. So if you just go back, then you will find that just remember those things. Then we were discussing about the bending stresses, and when a beam is there and it is under the application of bending moment. So due to the bending moment, just I am refreshing those things. Due to the bending moment, the upper area of the beam is experiencing these tensile stresses, and the lower area of the lower portion of the beam is experiencing the compressive stresses. But there are some locus of the points where there is no stress component, and due to that there is no strain is there. So but here you see the maximum when actually this and the same beam, when it is experienced by the shear forces, the maximum shear forces are at the neutral axis only. So see the comparison, we have F equals to dm by dx. That means you see here, whenever if I am saying that the shear stresses are maximum, okay, what about the bending moment or bending stresses, you see. So that kind of relation is always very important for that thing. So now come to that point, we have the shear stresses which is equals to 3f divided by 2bd. So in that also the maximum shear stresses which are occurring at the neutral axis is absolutely based on that how much shear force which you are applying, and then you see the two main dimensional parameter, that if you have more b or the height, then definitely the corresponding changes are there in the shear stresses. Now the mean shear stresses in the beam can also be defined as you see the tau mean, or we can say tau average. Generally you see we are using the tau averages which is equals to f by a or f by bd. So now it is this 3 by 2 times tau mean. That means you see what we have, it's a mean structure, means it's a simple f by bd. Tau maximum is we have 3 by 2 f by bd. So the relation is the maximum the shear stresses which are occurring at the neutral axis is 1.5 times or 3 by 2 times tau mean, or we can say the tau average. So this is exactly the this relation between the tau maximum maximum shear stresses and the average shear stresses which are occurring in the beam, the rectangular cross section of beam. But the important feature is that if you want to calculate the shear stresses maximum or first the normal shear stresses for rectangular cross section of beam, then first of all we need to find it out that what is the shear force is there and what are the dimensional parameter b and d, and then you see if we are calculating a normal shear stress, then only we need to know that actually what is the height or breadth and how much distance you see of this strip is there from the neutral axis. That means what is the value of y. But if you want to calculate the maximum one, because it is exactly at the neutral axis, so it is only we need to know that 3 by 2 f divided by bd. So you see these are the simple formula which one can easily calculate the maximum shear stresses which are existing at the neutral axis of the beam. So now you see, just keep those things in your mind. We would like to describe those things by graphical way. So we are focusing on the same rectangular structure which we used in the previous section. So we have, you see, this is a rectangular cross section, and we have this particular strip. You can see this is our matter of concern on which our focus is there. D by 2 is height is there, so total is the d height. Now at this neutral axis, as I told you, the maximum shear stresses are occurring. So the value of that is 3 by 2 f divided by bd. So you see here one can easily calculate this maximum, and since the distribution, if you just remember the formula, the tau which is 6f divided by bd cube into d by 2 whole square minus y square. That means you see the square terms are there. We have the distribution of shear stresses in parabolic way. So you see starting from because at these two extreme ends it's a 0 shear stress and it has a maximum value of the neutral axis starting from the 0 value. Now the distribution is a parabolic one, so now you can easily visualize those things. So this is the maximum value of shear stress. These are some average value of the shear stresses, so we can easily get those things because it is simply average value is f by bd, so it can be easily calculated. So it may be noted that the shear stress is distribution is parabolic as we discussed our rectangular cross section, and it is the maximum at y equals to 0, that means at the neutral axis, and the shear stresses are 0 at where you see this y is maximum, or we can say at the extreme corner. So this is a kind of shear stress distribution is there. Now so this all discussion which we made, it is just for a rectangular cross section which has a uniform structure. There is no and it has a symmetricity all across the neutral axis, so it is pretty easy to find all those issues. But now you see, if we focus on the I section, which has like a different segment altogether from the like the rectangular section. In that you see we have the two flanges and we have the like the web is there in between those things. So two flanges, even this structure is also symmetry. If you just cut the like this neutral axis right from the middle portion, then you will find that the one flange and half of the wave and half of the wave and one flange is there all across this neutral axis. So we can say that it's pretty symmetry. So you can see on your screen that we have the real feasible I section which we are using generally like for almost all kind of constructional way, that if we have like this I section there on our top of the roof or for balancing the roof, generally this I section is usable because it has a less mass moment of inertia, because what we are doing here in comparison with the like this rectangular section, the mass is very less. You see we are simply cutting those like the side mass from the web waves, so we have the less mass, and when it is like the inertia is there, inertia is very less as compared to that one, but like it has certain unique properties which we are going to discuss in the next sections. So right now you see we have the I section. So in that I section you see like again the same height is the D and the breadth is B. So in that this breadth is there of the flange. So for that, even this like the small height of the flange is the B. So the total I section height is D, but for these two flanges which have like both of the flanges have like the common kind of uniform structure. So for those things we can define a single parameter which is valid for both of the side. So we have, you see, the breadth is B for both section. This height is there for the flanges. The flange height is small b, and then you see we have the web. So for web also you see like what we have this this breadth is small b, and then like this height we can simply go with this small d. So there is a difference. Now if you are going for the overall picture, then we have the capital B and capital D are the dimensional parameter, but if we are going for the different sections of this I section, like for flanges, then we have, you see, the two main parameter, the small b and the capital B. And if we are going for like the web portion, then we have the dimensional parameter is small b and small d. So just keep these information in your mind. Now you see our main focus is we are again taking a small section of the like this I section. So for that you see here we have this small section of I which has the distance, you see, from neutral axis is y. So now here again our main focus is on this particular section, which is like this hedging section is there, that means the cutting portion which we are showing here. So now if you focus on these things, our main intention is to find out that how the shear stress distribution is there all along that. First we want to calculate the shear stress for this small element, and then we integrate those portion for the entire structure, because it is a uniform structure altogether. So the shear stress distribution for any arbitrary shape is like given as usual. General formula is F into A into y bar divided by Z into I. So now you see here focus on this our main because it's a rectangular this it is I section is there. So altogether you see our main focus is on the dimensional parameter. So now focus on the quantity AY, because for this case it comprises the contribution due to the flange area and the web area. So you see here it now our main focus is to combine the two different area altogether and then see the impact of these things, because in the previous case we had a uniform structure. That uniform means actually a simple structure which has like there is no kind of sections are there, that means there is no two different parts are there, just there was a one part rectangular part. But here you see we have in I section two parts are there, as I told you, one is the flange and one is the web. So now we need to integrate those things to calculate these stresses. So for that you see first of all our focus is on the flange area. So now if we are taking the flange, that means the upper part, we will find that like we have already described that the dimensional parameters are this capital B, and you see the total height, the top height is d by 2 from the neutral axis, and this one is the small d by 2 from the web portion. So now you see here if you want to focus on the height of this one, which like we assume that is the small b is there, even from that also we can calculate that this is capital D by 2 minus small d by 2 will give you the height, and the width is b. So area of flange can be easily calculated by b into d minus d by 2. So this is the area. Now you see the distance from like the centroid of these, just we want to calculate the y bar, that where the centroid is occurring, because now you see in the previous case it was pretty simple that okay now it is exactly at those things, but here you see we have a web and we have the flange. So with the consideration of these two different kind of sections, we can again calculate the distance of the centroid from the neutral axis, which is y bar equals to half of now this area of the flange which we calculated, d minus d by 2 plus d by 2, because you see here somewhere it is exactly exerting on this. You can see this diagram, it is here. So half of this d minus d by 2, so this height is d minus d by 2, half of this plus this distance d by 2. So if you want to calculate the distance from this neutral axis to any of the centroid, first d by 2 plus you see here half of this distance. So if we are like manipulating those things, we have y bar is equals to d plus capital D plus small d by 4, and then you see like we can also like just put those things there, then we can calculate the area ay bar flange, because that this is the main like the dimensional parameter is there for calculating the shear stresses for different sections. So as far as the flange is concerned, we have ay bar for flange is equals to b into d minus d by 2, that is the area, into d minus d by 4, that is the y bar. So it is, you see like this parameter can be easily calculated with the using of this dimensional parameter. Now the second section is the web area. So once you have the flange area multiplied by 2, you have the total like the ay bar for the overall both flanges. Now you see focused on the intermediate section, that is the web. So by considering web, you can see on your screen that the diagram of web, we have, you see the total like the total height is small d. So if you cut the neutral axis, then we have the d by 2. We have already assumed that the width of this is small b. And now you see here, if like already we put that the flange this flange and the web portion which is our matter of concern is having the height of y. So with the using of this information, now we can simply find it out that what will be the area of that. So now this particular this height is d by 2 minus y. So this is height, this is width b. So area is b into d by 2 minus y. So with the consideration of this area, now our focus is where the what is the distance of the centroid from these things. So again you see we are using the same information, that half of this portion particular, so half of this height is half into d by 2 minus y plus whatever the distance is there of this y, because you see this distance is there from the neutral axis. So this y plus half of this portion will give you the distance of the centroid from the neutral axis. So half of d by 2 minus y plus y, or we can say by manipulating these things, we have y bar equals to half of d by 2 plus y. Now you have area, you have y bar, you can calculate the a into y bar for this particular web portion. So it is pretty easy to calculate those things. So b into d by 2 minus y, that is the area, and then we have half of d by 2 plus y is the y bar. So now if we keep those things together, then we have like this area ay bar for this web portion. Now you see here, if you want to calculate for the entire region, means you see one web, two flanges. So for those things, ay bar total is nothing but equals to b, that is now for flanges first. So b into d minus d by 2, d plus d by 2 plus this the top portion which we calculated for the web, b is small b into d by 2 plus y, and you see like into the half of the portion. So like just manipulating those things, we have the total ay bar for web plus flanges is equals to b into d square minus d square. If you like if you multiply those things here, so d square minus d square by 8 plus b by 2 here, like you just calculate those b by 2, we have d square by 4 plus minus y square, because this is plus and this is minus. So a plus b into a minus b is a square minus b square. So now you see here we have the total this ay bar for both of the sections for one web, two flanges. So with the consideration of those things, now we are keeping like these things, these values in the main formula. We have tau which is the shear stress is equals to f by b into I. Like we are keeping those things b into I, because z is b, I is I. So now you see we are not like manipulating this I as like for these things. Till now you see we are keeping I as I, b is z. So like it is always coming like that. So this f divided by b into I, now this is b into d square minus d square by 8 plus b by 2 d square minus d square by 4 minus y square. So now you see here we have the shear stresses in that way. That means you see it is again, if you look at those pictures, then you will find that it is again going in terms of the parabolic path, because you see the square terms are there of the d square by 4 minus y square. So again it always reflect the kind of distribution of the shear stresses all along with the I section in terms of the parabolic way. So to get the maximum or minimum value of the shear stresses, again you see we need to keep those like the different boundary values constraints, and we can get those values. So at y equals to 0, that means like we are talking at neutral axis, the y equals to d by 2 at, you see now we have the two main condition. When we are talking about the y equals to 0, we have always at the neutral axis, and we know that the maximum shear stresses are always occurring at the neutral axis. So if you keep the y equals to 0, we have the tau maximum, that is f by 8, same you see this b into I, b d square minus d square plus b d square, because the y square has already gone in this particular first expression. So now you see we have the maximum shear stresses, and the other thing you see, if we are just going for the tip, that what will be the shear stresses at the tip, because the flanges are there at the tip. So we need to keep the y equals to small d by 2. So you see here the minimum stress is they are occurs at the top of the web, you know, like means you see just near to the flanges area, and the term b d square goes off, and the shear stresses is given as tau minimum, which is exactly at the y equals to d by 2, means the top of this web portion is equals to f by 8 b into I, b times of the capital B, that is the flange of the width of the flange total, into b d square minus d square. That means you see now you can pretty easily calculate that where the maximum shear stresses are there and where the minimum shear stresses are there. Meaning is very simple, these stresses are altogether varying with the web only. You can see here that at the neutral axis, which is passing from the web, is having the maximum, you know, like the shear stresses, that is equal to f by 8 bd, f by 8 b into I, you know, b times of d square minus d square plus bd square. So this gives you a maximum value which is occurring at the neutral axis. So you have the maximum, and then the parabolic distribution is there, and now you see we have the minimum value, okay, of this shear stress is exactly at the top and bottom of the web, means at d by 2 from both of the neutral axis, because we are assuming that it is a symmetrical section. By considering those things, now our focus is that now how the distribution is. So now you look at those things, that we have the same structure, you know, like this I section, this portion was which we covered, and then we integrated that part, this is the y distance, you go these things. So now you see here at these two portion, you see we have certain value, that is the tau minimum. So these are the tau minimum at these things as I discussed, and then we have at these neutral axis we have the maximum shear stresses altogether. And then you see, you know, like since this tau average, which we already discussed, that the tau maximum is 1.5 times tau average, so we can also calculate the tau average here. So look at this picture, we have a clear feeling that if we want to design any beam which has a cross section of I, then you see our main focus is to strengthen these you know, like the web portion, because you see here the maximum these you know, like the shearing stresses are occurring, and it's starting from these portions, that from the minimum section at the flanges part we have, you see, this web which is experiencing the maximum shearing stresses, and this maximum shearing stresses, the values are pretty simple, f by 8 b into I, into this b and I are just, you know, like these are the focused area or the focused parameters within the web portion, and then we have, you see, the region is coming within, you know, like in between the flanges and this web. So we have the capital B, that is the width of the flange, into d square minus d square plus b times of d square. So you see here we have a clear feeling about the shear stresses, that how, you know, like the variation of these stresses are there in that. So from the above distribution, we can see that the shear stresses at the flanges is not 0. They have the minimum values, and we discussed already, but it has some value, you know, like this can be analyzed from the equation 1, and at the flange tip, or we can say, you know, like the whatever the flanges are there or the web surfaces are there, at y equals to d by 2, we have certain, you know, like the value of this tau minimum which we calculated. And for the design purpose also, we need to be very careful that actually, though, you know, like we have the maximum shear stresses all along with the neutral axis, but these flanges are also having some effect or some impact of these shear stresses. So obviously then this will have some, you know, like the constant value, and then onwards this will have a parabolic distribution from that. So with that consideration, you see, again we have to be very careful that actually how the distribution is there, because you see in the if you look at those formula for tau minimum also, we have the square term, that means you see some sort of the distribution is there in the flanges also. Altogether you see we have a clear parabolic distribution in the web, but the distribution is there. So in practice it is usually found that most of the shearing stresses is usually about 95% is carried by the web only. So you know, like just 5% is there by both of the flanges. So you know, like when we are designing those things, one has to be very careful about the web portion, because it bears the maximum shear stresses and it is maximum at the neutral axis. Hence the shear stress in the flange is negligible. However, if we have concrete analysis, means if we are going for, that means if you just want to write the expression for the shear shear stresses for flanges and the web separately, we will have this type of variation, means some variation is you can see this thing. We have some variation in the flanges, but the real variation with the maximum value of the shear stresses in the web portion only. So, you see here, as I told you, that we have some sort of distribution in the flanges. So, the distribution in the flanges of this nature in the both of side, then we have, you see, this is starting from these, like since they have the square term, as I told you, that so that like since the square terms are coming in the tau minimum or tau maximum, means the minimum and the maximum value of the shear stresses, obviously the parabolic distributions are there. So, even in the flanges, though it carries only the 5% of the shearing stresses, always the distribution is the this parabolic one. So, this is parabolic here, and then you see we have the minimum tau minimum, this is one, as I told you, and it like describe the parabolic one with the maximum value at the neutral axis, and then we can calculate the tau average also once you know the tau maximum. So, this distribution is known as, this is pretty like the common phenomena, the top hat, because you see like the hat is on the top of that, and like the bottom side, you see even it follows a similar kind of structure like this. So, this distribution is known as the top hat distribution for shearing stresses. Clearly, the web bears the most of the shear stresses, obviously, and with the bending theory we can say that the flange will bear most of the bending stresses. So, this is a pretty like important phenomena. Just keep this thing in your mind, that you see whenever we are talking about the bending stresses along with the neutral axis, the bending stresses are not having the like the impact on the neutral axis. So, if you want to design for bending, okay, like the bending stresses are more, you see, and if you want to design any beam for bending portion, like you see for safe in the bending, always go for the this I section, because you see here the this loose portion is the Y, which carries the minimum bending shearing. Most of the like the bending is coming on the flanges part. So, that is why you see just make the flanges strong and go for this, and as I told you, see it has a less mass as compared to the this rectangular cross section. But if you want to design the beam for the shearing stresses, like here the weakest portion is the web, and in that the maximum shearing stresses are coming, the 95% of the shearing stresses are coming on the web. So, do not go for the I section wherever the maximum twisting or the shearing or the couple or twisting moments are coming in on the beam, otherwise you see the failure will be occur in that particular structure. So, this is as far as the practical applications are concerned, we are using correspondingly to the I section for like for this bending for the beam design for bending, and you see the rectangular section for shearing part. So, now you see here like so these two sections which we like we discussed about, this first was the rectangular cross section and second was the I section. Now, third cross section which we have the shear stress distribution in the beam for circular cross section. So, in the circular section again we need to like check it out that how the neutral axis is occurring, and like once you find out the neutral axis, then what the distances are there between the centroid and the neutral axis and how the distribution is there, that is our prime focus. So, let us find the shear stress distribution in the beams which has the circular cross section. So, in a beam of the circular cross section, again the value of Z will absolutely depends on the variation, because again this you can see on the diagram that this is the Z, Z is there, because you see here we are concerning about this particular strip. So, for this strip we have this particular Z which has the distance of Y from this neutral axis. So, here you see now this is the circular cross section which has the radius of capital R. Now, you see for that we are taking a strip which has a height, or we can say the unit width is there dy, and for that you see it has a distance from like the neutral axis is y, but you see the area which we are concerning, or the like the particular segment which we are concerning, which has the distance of y1. So, it has a variation from y1 to y1 is minimum to r maximum. So, you see here this is a pretty clear like the dimensional values are there in that what we are concerning. So, we are concerning about an area which or we can say the portion which has the minimum value of the distance of y1 from the neutral axis, and the maximum is capital R, which is like the radius of the extreme end. And then you see if you are concerning about this particular segment, let us say this segment which we are taking the one part of that, because it has a symmetricity on the other side, then we can find out this is the Z by 2, okay, and this distance is y. So, this in vertical distance we have the y, in the horizontal distance we have the Z, and this is you see like this is the radius is there from any, and this is our neutral axis is there for that. So, this is the main circular section of like the matter on which we just want to focus. So, using the expression for the determination of the shear stresses for any arbitrary shape as we discussed, or any section, this tau is equals to f into a into y bar divided by I into z, or we can say that you see here, since we are talking about like a circular section which has a symmetricity in all along with the radius. So for that, you see, now we would like to go for the first area moment, means you see we are not going for like the second moment of area, here the first moment of area. So here, just by describing those things, what we have f into a integration of, now y bar is simply replacing by integration of y into dA as usual divided by Iz, where y into dA is the area moment of shaded portion, or we can say that as usually the first moment of area. Hence in this case, you see the dA, which is like is to be very we can say like the main thing for shaded area portion of the area. So for that, you see, we are going to use the Pythagoras theorem, as I told you that we have a height of like this y, and we have this width is z by 2, because the z is the total portion, so half of the z by 2. So while applying the Pythagoras theorem for that particular portion, we have z by 2 square plus y square is equals to r square, or we can say that this z by 2 whole square is equals to r square minus y square, or we can calculate the z by 2, or z is equals to 2 times of square root of r square minus y square. So now you see we have, because this is the pretty typical phenomena here, that which portion you are covering according to the value of z is coming, as I told you. So here we are taking that particular strip which has like the width is dy, and it has a distance of y from that. So with that consideration, you see we have the value of z which is equals to 2 times of square root of r square minus y square. Now you see we can calculate like the dA area, because you see it is simply like the circular section is there, so it is equals to z times of dy, because z is the like the total height and the strip width is dA is there, so z into dy will give you the area dA. So now if you are keeping those things, then we have 2 times of square root of this r square minus y square into dy. So now you see like you have the area dA. Now we can again calculate like the mass moment of inertia I at like this at neutral axis for a circular section is pretty clear, pi into r to the power 4 divided by 4. So with that consideration, now going into the back, that what was the main formula? Formula was tau equals to f into a into y bar divided by z into I. So keeping those values there, in that what we have f as usual. You see now for the area, because you see as I told you in that particular figure, our minimum limit is y1, that one, and the maximum limit is r. So for entire region of this, we have the integration of y1 to r into now this area. So it is 2 into square root of r square minus y square into dy into this y is there. So with that, you see we have 2y into square root of r square minus y square into dy divided by, we have this z into this I. So z we have already calculated, this is 2 times of square root of r square minus y square into I, which is pi into r to the power 4 divided by 4. So keeping those values here, we have this expression now for a shear stresses, where you see r is the radius of the circle, and you see now as I told you the limiting conditions are from y1 to r. So we are keeping those things, and now by manipulating those things, like what we have 4 times of f divided by pi to the power r, pi into r to the power 4 into square root of r square minus y square. Now integrating, you see again y1 to r, this y times of square root of r square minus y square into dy. So now you see our expression is pretty clear now, that okay, now we want to define for these things, for this particular reason we have the like the kind of shear stresses of this nature. But you see this integration, like just keeping those things, that okay, now keep the y1 here and put the r1 value, we have like the final value of tau is equals to 4 times of f r1 square minus y1 square divided by 3 times of pi r1 to this r to the power 4. That means, you see now if you look at this particular picture, what we have this shear stresses which is depending on the shear forces F, but you see whatever the variations are there in the dimensional parameter, it is again in terms of the square term r square minus y1 square. So means, you see if we want to again go for the distribution of the shear stresses, again you see like it's a kind of parabolic distribution along with that. Now we would like to see that actually where the maximum and the minimum shear stresses are occurring, so that if we want to distribute those things, we have the clear picture that okay, these are the locations which are bearing the maximum shearing stresses of the circular section, and these are the portion where the minimum shear stresses are occurring. So for that, you see again like the similar kind of this theories are to be applied for calculating the maximum shear stresses or minimum shear stresses. Put, you see, for maximum value of the shear stresses, put y1 equals to 0, as you see in the previous case we put the y equals to 0. So by keeping y1 equals to 0, we have the shear stresses maximum, and which is equals to 4f times of 4 into f divided by 3 pi into r to the power square. So now you see here what we have 4 by 3 into f divided by pi r square. So if you want to calculate the maximum shear stresses, what we need to do, only we need to know that what is the value of the shear force and what is the radius is there of that, so that you see the distribution is coming accordingly. So by keeping those things, again our main intention is where this will occur, and this will occur because you see we are keeping y1 is equals to 0. So if you go for feasible, there is no distance between the minimum like the portion to the neutral axis. That means these shear stresses, the maximum shear stresses are occurring at the neutral axis only, and the value of these shear stresses which are coming at the neutral axis, which has a maximum like the value, and it has a parabolic distribution. So the maximum like the top of this parabola is coming exactly at the neutral axis, and the value of this is 4 times of f divided by 3 pi into r square. So now you see this is one portion which gives you like the maximum value. Now if you want to calculate the minimum value, for which you see like the diameter is y1 is equals to like plus minus r, the plus 1 is the top and the minimum is minus r. So if you are keeping those things, we have the, just if you keep those values, that y1 equals to r, we have tau equals to 0. That means you see here now clear like the description is there about, even if you want to calculate the tau minimum also, it is tau 0 at those extreme corners. Now you see distribution comes, then you will find that we have the maximum like the distribution all along with the neutral axis. The minimum values of these shear stresses are there exactly at the top of and the bottom corner. So now it's pretty clear distribution is there, the parabolic distribution coming right from the minus r to plus r like 0, and then it is going to the maximum at the neutral axis. Now you see if you want to calculate the average value of the shear stresses. So for that you see like again the average value, tau average or tau mean, is nothing but equals to f by a, or we can say that since it is a cross sectional area is the circular one, so f by pi r square. So now you see if you want to compare, then comparison in the previous case when the I section was there, it was 1.5 times of tau maximum, but here you see the tau maximum is nothing but equals to 4 by 3 tau average. That means you see like if you are keeping those things by 4 by 3, that means you see like by 1.33 times multiply the average value, you can get the maximum value. So you see now these all numerical values come into the real the graphical way, and the clear description is like that. We have a circular section of this nature at, as I told you, at plus r and minus r we have the 0 shear stresses, but the maximum shear stresses are coming all the way to the neutral axis. So this is the neutral axis and this plus minus r, and you see like it's a parabolic distribution was there which has the value of 4 like 4f divided by 3 pi r square. So with that you see you can calculate these like the parabolic distribution of the shear stresses which has the maximum value of, or we can say the top of these things, we have this 4f divided by 3 pi r square. So this is you see the shear stress distribution. So once you like know about like the shear stress distribution for any cross sectional area, you can design the beam accordingly, because the different portions are bearing like the different cross sections, the value of the shear stresses and corresponding factor of safety as, and the corresponding applications are coming all the way like how we can design those things. After that you see we have the principal stresses, because you see in this beam, as we got to know that the two main types of stresses are there. One is like the bending stresses and beam, which is like just all along to the longitudinal way, and we have another part is the tau, that is the shear stresses. So when you have like the normal stress component due to the bending, when we have the shear stress component due to the shear part, we can easily go for the principal stresses and in the beam. So it becomes clear that the bending stresses and beam sigma x is not like a principal stresses. Obviously it is a normal stress or flexural stress component is there, since at any distance y from the neutral axis, and there is a shear stress tau or tau x tau xy we are using for the plane stress component in x and y direction. So in general, the state of stress which we discussed in the initial lectures, like which has a distance y from the neutral axis, can be easily calculated, and you can see in this particular diagram we have a simple structure of this as usual, and you see this is our neutral axis which is passing from this, and if you are assuming that we have a cross section of beam is rectangular one, so this is the rectangular cross section, and you see it has a distance where you see we want to calculate the stress component is the distance of y, and this p value is, we can say, like where the centroid, or you see like the kind of this fibers are just passing on those things, and we want to calculate the bending as well as the shear stresses on that. So with the consideration of those things, you see again we can simply describe those stress component on the simple segment with the like the, as I told you, the longitudinal one is there at the bending. So these are the flexural stresses on all along with this particular like the longitudinal one, and we have the shearing stresses, this tau. So this is a perfect combination of the like the stresses of a beam which has like the rectangular cross section and carries both the normal as well as the shear stresses, shear stress component. And now you see when both components are there, we can easily go for the principal stresses, and for that you see again, first of all, as I told you, the normal stress component is coming due to the bending stresses, and with the bending stress formula tau by y is equals to m by y, we can calculate tau b, which is bending stress, is equals to m into y divided by y. And you see since the rectangular cross section is there, so I is nothing but equals to bd cube by 12. So we have, you see, the tau b, the sigma b is equals to 12 into m into y divided by bd cube, or with that particular, you see, we can again easily found the flexural stresses are all along with this particular x axis. So we have, you see, the normal stress component here with the value of 12 times of m into y divided by bd cube. But you see we have the shear stress component all the way, like from the complementary as well as the normal shear stress component, and you see the value of the shear stress component is nothing but equals to 6 times of f divided by bd cube and d square by 4 minus y square, because you see it has a parabolic distribution and it has a maximum value, see, all along that particular neutral axis. So we can calculate both the thing altogether, see. So we have the value of normal stress component, we have the value of the shear stress component. Now you see we know that now like if we have both the component altogether, so we can calculate the principal stresses sigma 1 or sigma 2, you see the maximum or minimum, you see, is equals to sigma x plus sigma y by 2 plus minus half of square root of sigma x minus sigma y by 2 plus 4 times of tau xy square. So now you see we have the standard one, but here you see, as you can see in the previous diagram, only we have the longitudinal stresses in the x direction only, so there is no y component, so sigma y will obviously be 0 because only we have the bending or longitudinal one in this x axis component. So sigma x is there, which is equals to sigma b, which is equals to 12 times of m into y divided by bd cube, and we have the tau 1, which you see, like in the previous section we shown you that it is 6f divided by bd square into d square by 4 minus y square. So from that you see we can simply replace those figures and we can get the tau 1 oblique tau 2, the minimum or maximum, is equals to half of, because half of sigma x plus sigma y is there, so sigma y is 0. So in terms of sigma x we can simply put this 12 times of my divided by bd cube plus minus half of square root of this sigma x square, that is 12 my divided by bd cube whole square plus 4 times of, you see, this tau is there, that is 6f divided by bd cube d square by 4 minus y square. So now by manipulating those things, what we have tau 1 or tau 2 basically is equals to x divided by bd cube. So you see, like it is coming out, and then you see in that you see we have my plus minus square root of, because m is the bending moment, it is, and due to that the bending stresses are coming, so m into y plus minus square root of, you see, like the m square y square plus f square times d square or 4 minus y square whole square. So you see here we have the clear picture that in the combined, you see, if you want to calculate the bending, this principal stresses due to the bending as well as the shear, it has a clear picture that both bending moment as well as the shear force is clearly influenced your principal stresses. And now you see with that, if you want to calculate the plane, that where you see, like these stresses are coming all the way, then you see that it's pretty straight formula is there, the tan 2 theta is equals to 2 times of tau xy divided by sigma x minus sigma y, since sigma y is 0. So you can put, like tan 2 theta is equals to 2 times of tau xy divided by sigma sigma a or sigma, like sigma x, you can say. So now you see here in this tau xy is again, like the same value 6f divided by bd cube into d square by 4 minus y square, and tau, like b, which is the bending stress, is 12 times of my divided by bd cube. So by keeping those things you can get the location of the principal plane there where these stresses are there, and you have both the value sigma 1 and sigma 2, so that you see we can easily get those principal stresses for this kind of. So now you see we would like to conclude this chapter that like we discussed the important phenomena about the shearing stresses, that it is very sensitive to which cross section which we are using, like like if you are using the rectangular cross section, or if you are using I section, or if you are using circular section, then how the distribution is there. Generally you found that like the distribution is circular and it has the maximum value like at the neutral axis only, but you see as far as this like the applications are concerned, again we are thinking about that like if you want to use any beam, then what kind of applications are there and how the bending as well as the shear stresses are occurring. And in the later section you see we discussed about the principal stresses, that if like if a beam is subjected by both bending as well as the shear stresses, then how we can get the value of the shear stress, this principal stresses, and at what location they are located. So this you see like all the way we discussed about the bending as well as the shearing stresses on a beam if beam is loaded with the point load or UDL like that. So now in the next section you see our main intention first like to use those like the formula for numerical derivations, that actually like will practicing those numerical problems, and then you see like we'll go for the further clarification about the deflections, that actually if the beam is there under this kind of load, then how the deflection will take place. Thank you.